Limits of a polynomial. On the screen, I have a general form for a polynomial. In general, a polynomial is just a sum of multiple terms. Each term can have a coefficient, like the c of n factor in the front, and it can have a factor with the variable, like the x to the nth power in this first term. And I've arranged them in decreasing order. So c sub n times x to the nth power plus one lower, so c sub n minus 1 times x to the n minus 1 power. We're not quite sure how many terms there are in this polynomial since we're speaking of it in general form. So we have these three dots to say many more terms could exist here, but that eventually this pattern would dwindle down to c sub 1 times x to the first power, and then c sub 0 technically times x to the 0 power, but x to the 0 power would just be 1, so we don't write the x term on that small term. So we have our general form of a polynomial, and we're going to talk about how to calculate the limit for any polynomial. If I want to take the limit of some polynomial p, so my function is called p, and my general form is this long expression of terms added together, then I can just take the limit of that same long expression of terms added together. Now, looking at that expression, I might think, I see a lot of plus signs here. So maybe we ought to try and apply the sum limit law. That sum limit law is going to break apart each and every one of these terms so that instead of one long expression, I have separate expressions. So now every term in that general polynomial has its own limit notation on it, thanks to the sum law. Once we've broken apart the sum law, I see that there is a constant multiplier on each one of my terms. So we can use the constant multiple rule to factor out the coefficients. So now you see that the coefficients are on the outside of my parentheses, the limit symbol is inside. And then lastly, I see that there's powers on each of these functions that I'm taking limits of. So I can use the power rule to place the exponents outside of the parentheses. And so we've broken it apart completely. We separated every term so that it has its own limits. We factored out any constants, and we removed or pushed the exponents to the outside. And the reason for that is that now we have the basic limits isolated. So in these first three limits, we're looking at the limit of the basic function x, where x is approaching a. We know each one of those is just going to be equal to a. The last limit is the limit of a constant. C sub 0 is some fixed constant, so it doesn't matter where x is going, c sub 0 is going to stay c sub 0. So lastly, we can replace each of these limits with their values. And after that, we can simplify. And then we notice that what's on the right-hand side, it looks awfully like what we started with at the top of the screen, but all we've done is replace the x's with a's because our limit had x approaching a. And so, what we know is that if we're dealing with a polynomial and we want to compute the limit of it, we do not need to go through every tiny detail using the sum law, the constant multiple law, the power law. Instead of using all three of those and writing limit, 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 we can jump straight down to the bottom and say, oh, the limit of a polynomial, where is x going? X is going to a? All right, let's plug a into our polynomial. So we're just going to kind of plug and chug, which is really great news. Let's go ahead and try one. On the screen, we have the limit as x approaches -2 of the function 4x squared plus 2x plus 1. Now, instead of applying each of those limit laws individually, we're going to say, hey, that is a polynomial, and if the limit is having x approach -2, then I'm just going to replace the x's with negative 2. So I'll have 4 times negative 2 squared plus 2 times negative 2 plus 1, and then we'll simplify. Negative 2 squared is equal to positive 4. I have 2 times negative 2, which looks like negative 4. 4 is 16, minus 4 plus 1. 16 minus 4 is 12, plus 1. So even doing that very slowly, step by step, that was a whole heck of a lot faster than applying the 3 separate limit laws, the sum law, the constant multiple law, and the power law. Now that we know that the limit of a polynomial is equal to evaluating that polynomial at the value x is approaching, then we can talk about rational functions. And the reason why is because a rational function is made up of 2 polynomials. So if you have a polynomial for the numerator and then a polynomial for the denominator, then you're talking about a rational function. Now, the only time that we would have a problem is if the denominator is equal to 0. That's always been an issue. That's not going to change today. So let's make sure that our rational function is defined. We don't want to have our polynomial in the denominator equal to 0 at the value that we're trying to approach. So for our rational function, we have p on top, the polynomial p on top, q on bottom, that's another polynomial. Together they make up a rational function. We're allowing the limit of x to approach a. And what we're saying from this slide is that we can simply replace p of x with p of a since x is approaching a. And we can do the same thing in the denominator. This is one of those things where you spend a little bit of time on one fact and then the next fact comes kind of for free. So let's go ahead and evaluate the limit of a rational function. The limit here has x approaching 3. The rational function has 2x squared minus 3x plus 1 on top and 5x plus 4 on bottom. So what I'm going to do is simply take all of the x values and replace them with 3's. And then from here we'll simplify further, starting with our exponents. 3 squared is 9, and we can multiply things out if we're ready. Moving on to our denominator, simplifying even further. 18 minus 9 is 9, plus 1. In the numerator, we have 10 over 19. So again, even doing this in the very long drawn-out way that I did, writing every single step, still way faster than applying the limit laws, including the quotient, sum, difference, constant multiple, and the power rules. So much faster now that we know that when we evaluate the limit of a polynomial, we're really just evaluating the polynomial at the value that x is approaching.